Hello students, today we're going to talk about acids and bases and pH. Before we can do that, we need to have a good understanding of equilibrium. And so let's take a look at that. We have in this picture a reaction of N2O4 to make 2 moles of NO2. If you don't mind, I'm going to switch from this red to a purple. Okay, so think about how reactions roll. Normally, we start off with only reactants. So, of course, this is going to shift right to make products, correct? Got to go forwards. So, we would say that the reaction shifts right. And what I mean by that, it's going to go forward, it's going to get consumed, it's going to decompose, okay? So, and initially, it'll do so pretty fast. So we're going to talk about speed of reaction. This will not be the first time that we talk about it. We're going to come back for a more thorough discussion after exam 1, so for the next section. But for right now, realize that the rate is the speed of reaction. And at first, it's going to be fast because that's all you have is reactants. And it's going to depend on the concentration. And there'll be this constant, which is called Kf, which means forward. The F is forward. K is a little constant. It's called the rate constant. And that is one thing we'll talk about more later. But what I want you to realize, let's look over here at the graph, that initially we have N2O4, and then it starts to decompose, right? So the amount goes down. At first, let's look at this other graph with the rate. At first, the speed's pretty high, and as it keeps going, the reaction progresses, the reaction starts to slow down going forward. Okay, now this is a kind of reaction that is very interesting because as NO2 accumulates, the reverse reaction kicks in and it shifts left. And we can talk about the speed at which the reaction goes reverse. Now, for now, realize that I'm going to pull that 2, that coefficient, as a superscript. But that's not so important at the moment. The idea, though, is to understand that NO starts off at 0 because it wasn't there. We only had reactants at first. And then as the reaction proceeds, more of it occurs, right, is formed. So NO2 increases, but some goes back to form products. And so here, Kr NO2 squared, this is the rate. The rate increases, gets faster going backwards. Eventually, the speed at which it's going forward equals the speed it's going reverse. And that's a famous thing in chemistry called equilibrium. That's the rate forward equals the rate reverse. Okay, now at equilibrium, couple things. Let's take a look. At equilibrium, the rate, I've highlighted here, the rates are the same, reverse and forward. That's the definition. If we're looking up at the top one, when equilibrium's achieved, you have a certain amount of N2O4 in there and a certain amount of NO2. So their amounts are, in this example, not necessarily equal. If you notice, you have more NO2 than you do N2O4. But what I want you to understand is that since this reaction goes backwards and forwards, it's essentially what's known as a reversible reaction. And at equilibrium, we have a little bit of both. You know, we have NO2 and N2O4 present. So this picture here at the top is trying to show us, if you look at it carefully, that in the reaction flask, we have N2O4 and NO2 present at equilibrium. They're both there. Okay, so let's keep going with this idea. That's the conceptual side of equilibrium. There's a quantitative side. And the quantitative term is something called the equilibrium constant, K. And it's the ratio of products over reactants. So this is the important part, is it gives us a really good indication of what's going on once equilibrium hits. Now, if I have a generic reaction of A going to B, then the K equilibrium, I'm going to call it Kc. The C will be for concentration, but there's all sorts of K values. There can be Kp, for example, for pressure. Later Ka for acids, but regardless of what that subscript is, it's the ratio of products, I'm going to show B, over reactant. And this idea is called the law of mass action. The only thing that you need to also consider, though, is let's go to our N2O4 example. This would be Kc would equal the concentration of NO2 squared over N2O4. So the law of mass action is going to require us to take into account the coefficient as the superscripts. Okay, and where did this get derived from? If you want to ask me more of that in the video in the Zoom discussion, that's fine. It has to do with setting those rates equal to each other. So this will just be a note. I won't ask you to derive it though. We said K forward was this, and K reverse was that. So that's the definition at equilibrium. And then we could combine the K's algebraically. Don't get scared. I'm not going to ask you to do this on a test or anything. But you see how these K forward over K reverse, that would essentially be a new K is given as big K, K equilibrium. Okay, so that's just a side note. All right, so now let's talk about what the magnitude of K will tell us. So if we have a reaction where A goes to B, and then B loves to go backwards to form A, and then the rates hit, and it's going back and forth, and those reactions are pretty much equal in strength forward and back, then what you'll end up with is a Kc where you have relatively equal amounts of B and A. And in this scenario, for a reversible reaction, the K equilibrium then is going to end up somewhere around 1. Now, technically, if we wanted to get very technical here, a Kc of around 1 is really more like, it's a wider range than that. So like it's really 0.001 to 1,000. But for us, really, we just want to understand that reversible reactions have Kcs that are around 1, and we consider that a moderate Kc value. Now, if you're thinking of this in terms of chemistry and making stuff, if we want to make B, we want a high amount of B, we'd have to figure out a way of shifting it towards product. And this is something that in biochemistry will be so critical because there will be a lot of reactions that we encounter in metabolism that are reversible, but we want them to go forward. And so how are we going to do that will be the pressing question later. Okay, there's also a different kind of reaction type. This is one that you're more familiar with from your previous chemistry. These would be product favored. Equilibrium lies far to the right. Something like a combustion. It's a great example. Burning something. In a combustion reaction, you will not see written in a book the double arrows because in theory, there's a reverse reaction, but it's very negligible, really non-existent. So when we write the Kc value for this, when equilibrium hits and those rates equalize, you're going to have a huge amount of B. And what does that mean? Is that Kc will be gigantic. So a good example, another great example of this would be redox reactions like in batteries, like your lithium ion battery in your phone. The Kc values for ones like that can be as large as like 10 to the 54, 10 to the 60, gigantic values, meaning that they like to go one way. They like going forward. So forward reaction is favored. Okay. You can have a scenario where A forms B, but then B loves to go back. And so it's much stronger going reverse. Oops. And so I would just going to draw a little arrow going forward. Oops, I'm still on. So a little arrow going forward, because really what dominates is that reverse reaction. And in this case, if we look at Kc values, what we'll see is that we have an enormous amount of A when equilibrium hits. And so this will make Kc very small. So small Kc values would be things like, gosh, they can get as low as like 10 to the negative 34. You can have 10 to the negative 12. So Kc values can be very, very tiny. So reactions will fall into one of these two categories. The easiest one to do experimentally would be, if we have, I'll just put as a side note, the Kc around 1, the Kc greater than 1, and the Kc's smaller than 1. Out of the three, the one that's easiest to do experimentally is the second scenario, right? That guy is product favored. Oops. The other two are not product favored. So the question later for us will be, how can we get reactions that don't want to go forward, move forward? Okay, and that's going to be a discussion for us later as we keep going in this class. Now, before we move on, the K-equilibrium or Kc value, let's start with the second one. I'll number these 1, 2. Products over reactants. So if you want to pause me right now, that's good, and do number 2. That's going to be SO3 squared divided by SO2 squared times oxygen. Okay, so we'll take into account the law of mass action and include our coefficients. Okay, let's look at the top one. Now, in theory, we would include everything that's written there. So product over reactant. Okay, so I put the 2 for the HCl moles. Now, here's the deal, though, is concentrations, molarity, right? Moles per liter. We tend to describe with solutions. So things like aqueous, right, are aqueous ones. And then we also describe gases because they're dilute. They're very dilute. It would be odd, if you think about it, for me to ask you the concentration of a sample of water liquid or the concentration of a solid. And so what we will see, and I don't want to spend too much time deriving it because it gets very confusing for students. It's just better to think of that we don't talk about the concentration of a solid. We have so much stuff usually there that the number of moles and volume is very high. And so what's going to happen is we don't show those solids or pure liquids. Pure substances are not shown in our Kc expression. If you want in our Zoom discussion, you can ask me more to derive it if you're very curious. But the idea is that if we do, I can do that for you in the Zoom discussion. I can show you what a concentration of 1 liter of water is, but you'll see that the number is massive. And so in the course of these equilibriums, it's essentially a constant, and those guys get absorbed into Kc. Now, I won't ask you to explain that. The only thing I really need you to be able to do is to write the appropriate Kc expressions so that later when we see them as part of a biochemistry discussion, you understand what it is that you're reading. So just include aqueous and gases. Okay, Le Chatelier's is a huge topic for us. And for right now, I'm going to just define it for you. We're going to do a quick example. But in the next video lecture 3, we're going to spend a lot of time on it. So this is the idea that equilibriums can be shifted. You can shift them right towards product, you can shift them left, it depends. So let's say that I have a system in equilibrium. If I add A, then that system wants to get back to equilibrium, and I would have messed it up by adding A. So it's going to shift away from what is added. So that's this first one. That if we add a reactant, it's going to shift away from that towards product. So this is going to shift right. By shifting, I mean reacting to make product. Okay, I could add B. I'm going to rewrite it. Okay, if I add B, doesn't matter that it's a product, it's going to shift away from what's added. So it's going to shift left. Now, keep in mind that these guys would have to be gases or aqueous, so it has to appear in our equilibrium for this to be true. So solids and liquids, this doesn't apply. Okay, now, what if we remove something? So let's say I remove B. Well, if we remove B, I think that arrow makes it look like I'm adding it, so I'm going to change it. Oops, I need to highlight, sorry. I'll just put remove B. This is going to shift to replace it, so it's going to shift right. So that's the second one, that Le Chatelier says that it's going to shift towards what's being removed. The idea, though, and this is really important, is when we do these shifting, adding, removing, Kc stays the same. The only thing that changes Kc is temperature. So I'll put that up here. Now, this is very important. If this was a general chem class, we'd go into temp and we'd talk about this shifting this way with temp. None of that's relevant in biochemistry, because if, let's say, you are going to start jogging and you need muscle contraction, you do not press a button on your arm to change your temp to metabolize more glucose. You can't do that. We have to stay at a relatively constant temperature. In fact, as we move out of normal range, we get fevers, we can get very sick. And so high temp is not a good thing for our bodies, right? We have an infection. So what I'm trying to say is that temperature for us in biochemistry is not really important, because we cannot manipulate our body's temp to make more product of something. So in the body, we have to find ways to shift towards product, shift to the right, that does not involve lowering or increasing temperature. And for that reason, I'm not going to go into the whole temperature thing. Okay. All right. Now, in the next video lecture, we'll talk about how we can apply this to the bloodstream biochemistry. And I love that example. It's a lot more interesting than the A or B, but that's its own separate little discussion. Okay. Here's one, nitrogen and hydrogen to ammonia, an example. Ammonia is very important in industrial chemistry. So let's say I want to know how I can maximize the amount of ammonia. If I want to maximize how much ammonia we make, that means we want to shift to the right. To do that, we would add nitrogen or hydrogen, because that is going to, according to Le Chatelier's, that's going to shift towards ammonia. Conversely, the way they do it industrially is once they make them in a giant container of ammonia, but then they remove the gas out of that container, because once you remove ammonia, it's going to try to replace the ammonia that's been removed, and it's going to shift right. Okay, So that's an example of Le Chatelier's, but we're going to do bloodstream biochemistry, which I know you'll enjoy, but that's the next video. Okay, acids and base discussion, super important. Please review your acids and bases and understand their formulas. So an acid's a proton donor. Strong acids dissociate completely, 100% ionized. There are only a few strong acids, HCl, HBr. Is it okay if I don't write all the aqueous in? HI, HNO3, HClO4, H2SO4. Some textbooks include HClO3. Okay, so these are our strong acids. Now, the truth is that in biochem, we are mostly concerned with weak acids. But weak acids, how do I spot them? There's hundreds of them. So the best thing to understand is if it's not on our list of strong, then it's a weak acid. Weak acids are not ionized 100%. The blanket statement would be less than 10% ionized, but it really depends on the concentration and which acid it is. So this is not something we can just eyeball. We can't say, oh, acetic acid's 2% ionized. This requires more information. Okay, so I really need you guys to remember some important definitions. And the Bronsted-Lowry definition is one that we are going to use. And that is the conjugate acid base pair definition. So we're going to have HC2H3O2. That's our acetic acid. Do you remember that one? And so it's our weak acid, and then its conjugate base is acetate. And the base pairs differ by 1 H plus. So this is the acid, and this is the conjugate base. Okay, we're going to keep practicing that here. When we're talking about weak acids, they are in an equilibrium that we can describe. So let's take, I like to use the acetic acid example. I'll write it here. The acid reacts with water to form acetate and hydronium. Okay, so this is where your previous knowledge becomes more critical. So I'm talking about this like you remember some of this, right? So if you don't, then you're going to need to work a little bit harder to get caught up again. So remember that acids donate H plus to water. Water's the acceptor. And then you form hydronium, H3O plus. Acetates the conjugate base to the acid. And I want to check something because okay, I did write it. I didn't remember that I had written conjugate base. Okay, so couple things are what we're forming are charged species, ions. So please don't forget their charges, right? That if the acid loses H plus, what is left behind has a negative charge. And then we can, and I'll put this in, we'll write it out. So for this particular acid, this would be acetate, hydronium over acetic acid. Okay, couple comments. Always in chemistry, H3O plus is a more thorough way of writing acids in water because H plus doesn't exist without latching onto the water that's there. But these are used synonymously. And so H plus, H3O plus, they're used interchangeably. But keep in mind that the Bronsted-Lowry definition, which is this one here, is just a much more thorough way of writing acid-base chemistry. Okay, now this is a weak acid. So the question is, if it doesn't ionize very much, which direction will this equilibrium lie? And if you said to the left, that is correct. So let's go to the next slide. This is a very important slide. And what it's basically telling us is that we have our acids there. Those are very common biochemistry acids. So these are important ones we're going to see in the semester or talk about. Phosphoric, lactic acid, carbonic, ammonium ion. Okay, formic and acetic, I wouldn't say are as important in biochem, but I've highlighted the ones, here I'll highlight all the ones there that are very common biochem acids. Now, when we talk about them, we will talk about their equilibrium. And so I'm just going to compare a couple of them to each other. Let's look at phosphoric acid because it's such a common discussion in biochem. Okay, it's going to lose one H plus. So one less is H2PO4 minus. All right, it's Ka. I'll write it up here. Give me more room. Product over reactants. No water liquid. Okay, its Ka value, let's look on the chart, is 7.24 times 10 to the negative 3. Okay, now it's part of a family of acids because H2PO4 can lose another proton, another H plus. Okay, go ahead and write pause me so that you can write the product. Now it goes to HPO4 2 minus. And let's look up that Ka, 1.38 times 10 to the negative 7. And lastly, HPO4 2 minus write it in from the chart. Okay, so all three of these are not on our list of strong acids, correct? So they are not strong acids. They're all weak, but they're not all equally weak. And that's the important part of this slide, is the smaller the Ka, the less ions, the weaker the acid. And I can't stress how important it is to know that for things that we're going to do in biochemistry. So the smaller the Ka, the weaker the acid. So out of these three, which one's the weakest acid? HPO4 2-. Okay, so that guy's the weakest acid out of the three weak acids. So they're all weak. That's the weakest. Okay, and we know that because let's take a look at its Ka value. Okay, that is a very small Ka. Tiny, tiny. Okay, the other thing, couple other points, is each of these is a separate acid system. So H3PO4, its conjugate base is H2PO4 minus. Its conjugate is not phosphate, only one H plus at a time. H2PO4 minus, its conjugate is HPO4 2 minus. And then HPO4 2 minus, its conjugate is PO4 3 minus. So these are three different acid conjugate base systems, each with their own Ka. We don't mix and match them. That's number one. Notice every time the acid loses an H plus, the ion gets a negative. So it goes to H2PO4 minus, the first one. Then on the second ionization, it goes to a 2 minus. Okay, so every time it loses H plus, it gets more negative. Lastly, if we're comparing these three acid-base systems, the Ka is only a little bit helpful in the sense that it's very cumbersome to talk about. So talking about Ka1, 7.2 times 10 to the negative 3, that's hard to reference. So instead, what we talk about is something that you absolutely need to know, which is called a pKa. Which is the negative log of the Ka. And the negative log of the Ka is the pKa. This is just a math manipulation to convert awkward numbers with the exponents that are negative to numbers that are easier to talk about. So take a minute, if you could get a calculator. Let's go ahead and calculate the negative log of these three Kas. And they're shown in this table, so you need to double check them if you can come up with them on your own. So, the first one is phosphoric acid, 2.14. That's the negative log of 7.24 times 10 to the negative 3. Make sure you can do that in your calculator. The pKa of the second buffered system is 6.86, and the third one is 12.4. And so make sure that you know how to do that. I can write the first one in. So for the first one, pKa will be negative log of 7.24 times 10 to the negative 3. And so what I want you to see is another very, very important relationship. We said that the smaller the Ka, the weaker the acid. Okay, the smaller the Ka, the weaker the acid. But let's look at the pKa numbers. They get bigger. So the greater the pKa. And this tells us a lot about the acid that we're looking at. Okay, so I would say that this is something for sure that you need to know and be able to discuss. We use pKa's a lot this semester. A lot. Okay. Okay. Let's go to the next one. So why is pKa important? Again, that it'll tell us, it gives us information of acid strength. The smaller the Ka, the greater the pKa, the weaker the acid. Not all weak acids are the same, as that's what we just saw, right? Some are weaker than others. Okay. All right. This will not be the last time we talk about pKa's, so make sure that you really understand this section. Bases, strong bases, NaOH, metal hydroxides, and then weak bases. The most famous one is ammonia, NH3, does not dissociate completely. We can talk about KBs, the equilibrium constant for base, products over reactants. And then just remember, though, that our equation is NH3 plus water to make NH4 plus hydroxide. And so looking at this, then, why is this? Because we have NH3 has that lone pair on the nitrogen, and so it's going to accept H plus from water to make ammonium ion. And hydroxide. Now, looking at this, there's one thing that I need you to know that's very, very critical for later discussions. It'll make things make a lot more sense. Is NH3 is neutral. And what we're seeing there is that nitrogen has 3 bonds. Now, you might have learned in your previous chemistry something called formal charge. I want to keep it a little more simple than that. So let's just say when nitrogen has 3 bonds and a lone pair, it's neutral. When it has everything bonded, the charge on that nitrogen is +1. Now, I suppose I could do the formal charge thing if you just want a little bit more thorough and not just memorize, but what formal charge is we take the number of valence electrons and we subtract off an assigned number. This gives us an indication of the electron charge distribution within that molecule. So I'm going to pick, I guess, a little bit different color. Let's go with green this time. Okay, so if you want a little bit more thorough understanding of why the one's neutral and the other one's a +1 charge, we can do the formal charge. So nitrogen, if you had a periodic table, you'd see had 5 valence electrons. So both of them 5 valence. And then I'm going to assign a number. The assigned number goes like this. You can watch me. 1 each for every lone pair electron. So that's 1, 2. 1 for each bond. 3, 4, 5. So my assigned number is 5. 5 minus 5 is 0. That's why it's neutral formal charge, saying that it's even, the electrons are evenly distributed. Okay, in the case of NH4, the assigned number is 1, 2, 3, 4. That gives us a +1 formal charge. Now, this is going to be important because the NH3 discussion comes up all the time in amino acids. So I need you to understand that if you see NH3 by itself as ammonia, it's neutral. But once nitrogen has 4 bonds, we will always show it as a +1. Okay,